handling the chat. I'm not actually able to see it right now. You can just give me a thumbs up.
Yep, I can handle the chat. Sorry.
Okay, terrific. Thanks. All right. Okay, so remember that we talked about this is straight from our notes from last week, so you don't feel like you need to. You don't have to copy this if you don't want to. We're going to go with green today. All right, pressures at the same elevation are the same. Ooh, that's a little lighter than I thought it would be. Sorry, a little hard to see. Let's do. We'll just go with black, I guess. They are the same when in same fluid. Oh yeah, I caught myself. I'm going to try to fluid. In other words, that fluid is all connected through the manometer. Okay, so I'll try to write in caps so that this is a little easier to see my writing. If you move vertically down in a system, so in other words, if we're going from this elevation, so this pressure and this pressure, PA is equal to P1 according to rule number 1. And similarly, we would also say that P2 is equal to P3. So 2 is right here, 3 is at the same elevation across. Now, the reason we're using this interface is that we're just sort of able to skip everything going on down here. We would subtract some stuff and add it back up. But when we would add some pressure and then subtract it over on the other side. But basically, we can just jump over from 2 to 3 in this case. We couldn't do that right in here necessarily, or we could, but the problem is that we have this differential value here. So we're just going to go from 2 to 3 with because we're in the same continuous fluid. So if you move vertically downward, then remember you add pressure, and when you move, so in other words, P2 from this rule, P2 will be greater than P1 and also PA if we wanted to go that far. And if you move vertically upward, then you subtract, or we could say lose pressure. So in other words here, we would say that P, I'm going to call this point number 4 here, P4 is less than the P at 3, right? Okay, so that was our overall view. This is sort of a pretty simple setup. What happens when we get into the systems of manometers that are in particular at an angle? The same rules apply. We just need to be careful about our geometry. Okay, so here we have an inclined differential manometer where we're looking at the difference between the pressure in A and the pressure in B. These are two different pipes. They both carry brine. So brine is just a fancy word for a very salty solution. But this manometer fluid, in this case, is carbon tetrachloride, okay? So we're going to have some gamma CCl4, that's the chemical name for carbon tetrachloride. And then we will, up here, we'll say that we have some gamma Br for brine, okay? So that will apply both in pipe A and pipe B, where the blue shading until we get to this line. And so prior to, well, let me read the rest of the statement here. Initially, the pressure differential between pipes A and B, which contain a brine, is 0, as illustrated in the figure. So in other words, PA is equal to PB, and this interface is at the same elevation as this interface on the other side. Okay, so we could write, I'm just going to write this equation before we read the rest of this. PA plus, some height here. I will just call this some HI. So times gamma oh,
Yes.
whoops, gamma brine
I have
times
food. I have calorie and I have fat. Sorry.
HI, pardon me. And then we would go across
Yeah.
through the manometer. We don't actually have to use
Yeah.
carbon tetrachloride because our interface on the left-hand side is the same as the elevation as on the right-hand side. And then to get to B, we would say minus gamma brine, and then also times H sub I. We could otherwise put H sub I in some sort of length context to get out here and use some trigonometry. But then we would say this is equal to P sub B, okay? Now, ultimately, this cancels with this, right? One's plus, one's minus. And before we read the rest of this, PA plus, some height here. I will just call this some HI. So times gamma, uh, gamma brine times HI, pardon me. And then we would go across through the manometer. We don't actually have to use carbon tetrachloride because our interface on the left-hand side is the same as the elevation as on the right-hand side. And then to get to B, we would say minus gamma brine, and then also times H sub I. We could otherwise put H sub I in some sort of length context to get out here and use some trigonometry. But then we would say this is equal to P sub B, okay? Now, ultimately, this cancels with this, right? One's plus, one's minus, and we just say, we prove to ourselves PA is equal to PB. But we could do that with the rules that we had on the previous slide, okay? So now, this question, though, says our brine specific gravity is 1.1, so it's more dense than water, 10% more dense. And we start out at 0. Now, what we want to do is we want to have the manometer give a differential reading of 12 inches over on this right-hand side. So in other words, the manometer now, this level is going to move down. That's not quite right. This level is going to move down, and this level is going to somehow move up, so that the difference between them is 12 inches over on this side, okay? Now, that's a little bit funky, and you can imagine that that 12 inches is not perfectly vertical, right? Because it's going along the length of this manometer that's at an angle, we'll need to invoke cosine or sine to help us out with this, okay? So we'll set up the geometry in a second. But this delta L, this change in length, along the slope manometer will give us 12 inches, all right? But when we have that 12-inch change, the pressure differential will be 0.1 psi. So the question is, determine the angle of inclination. What is theta? So you can see it indicated right here. What is theta for delta P between A and B of 0.1 and this 12-inch change? In other words, for a really small change in pressure, you can see we have a really big change in our delta H here. All right. So let me advance here so that we have some room to work. All right. I left the small version of this on the left-hand side just so we can keep it for reference here. Note that gamma CCl4, our carbon tetrachloride specific weight is 99.5 pounds per cubic foot. Okay, so we're working in English units here. And one thing that I want to point out is that along I'm going to indicate this change here as A, and I want to indicate this change over on the right-hand side, going from here to here, as B, okay? So B is not a height, B is a length along this this angled manometer, all right? So delta H, we said this, or delta L, pardon me, delta L, it's supposed to be a delta. Delta L is equal to 12 inches. Ultimately, that's what we want, is some 12-inch difference here. But that 12 inches is made up of two things. It's equal to B, this difference of the move up, right, of the fluid going from here to there. But then there's also A dropping on the left-hand side. So this is going to be equal to B plus, and then we're going to say A over the sine of theta. Okay, why did I indicate A over the sine of theta? The reason I did this is that essentially the sine of theta in this case, when we look at a triangle that has A on one side, it has some B over on the right hand side. We basically are going to have the opposite over the hypotenuse, right? The opposite of this angle, and this angle is this value here, this theta down here, right? So there's theta. Sorry, I realize it's getting a little jumbled, but anyway, sine of theta here is opposite over hypotenuse for our idealized right triangle. So this would be basically the whatever this hypotenuse length is would be equal to let me rewrite this. The hypotenuse, I'm going to put this on the left instead, is equal to A over the sine of theta. So A is our opposite length, right? A is mirrored over here. B is not quite our full length there. It's actually this hypotenuse length is going to be this delta L plus B, I believe. That's right. But anyway, for now, let's just leave that alone for a second. We're going to leave L in this term right here, okay? And we'll come back to this equation. But that's the first thing that we can write. All right, the second thing we can write is to now note the changes. So we just went through a really simple way of saying, okay, PA is equal to PB, and we sort of did that the hard way. But what we need to indicate now is that there's a change in PA. There's some new pressure that is going to come up, and there's also going to be a new pressure at B, but let's work our way through the manometer in this change condition. Okay, so A has been added to the brine height on the left-hand side, and the carbon tetrachloride has moved up to this level over here on the incline manometer. So now P prime A, so in other words, a new pressure at A, is going to be, we're going to add to that the brine height to get down from here to there, okay? The brine height of, I just want to make sure I called this H sub I, right? Okay, H sub I plus A, okay? So that takes our pressure down to here. Now, if we go all the way across, we can start from here, from this location, but we need to go up to that value there, and we know that that total length is 12 inches. So what I'm going to do is we're going to subtract now gamma times carbon tetrachloride. So that is our specific weight of our manometry fluid. And now we write in that basically this height, the height of this change here is what we need. And that height is equal to A plus B times the sine of theta, okay? And this is just basically giving us the vertical elevation here, A plus B sine theta, which will not equal, this is the vertical part of what that 12 degree or 12 inch change along the length of the manometer is, all right? So we add that, we subtract that term, and then we also need to subtract whatever is left over to get up to HB. So now we subtract, or not HB, the middle of pipe B here. So now we're going to subtract the brine specific weight And then we started out at HI, and we're going to subtract this B sine theta that has changed along the length to give us PB prime. Okay, so this is working our way through the full manometer with this changed elevation. On the left-hand side, where the brine moved down from where we started, a distance A, and then on the right-hand side, we moved up some length B with our carbon tetrachloride and shrunk the column of brine on the right-hand side. All right, so now I'm just going to rearrange this and expand it, and then we'll simplify. So PA prime minus PB prime, I'm going to keep those on the left-hand side, is plus, I'm going to multiply this out, gamma BR, that's supposed to be a B, boy, that looks terrible. Okay, BR times HI plus gamma BR times A minus gamma CCl4A minus gamma CCl 4 times B times the sine of theta. And then I expand this final term here. We have gamma BRHI minus gamma BRB times the sine of theta. Okay? Now, what you'll see is that we can cancel a couple of these things. This term, let me get that right. Here's a negative gamma BRHI and a positive gamma BRHI. Okay, so those will cancel, which is helpful. And then the other thing you may note is that we have a gamma BRA and a gamma CCl4A, a gamma CCl times B sine theta, and a gamma BR B sine theta. So what we could do is then group this and simplify again. So PA prime minus PB prime plus gamma BR, all I'm doing is grouping the BR terms again, these brine terms, A plus B times the sine of theta minus gamma CCl4 times A and then plus B sine theta. That's right. Yep. Plus B times the sine of theta. Then gives us, I forgot to complete this up here. This is equal to 0 because we moved the PB prime to the left-hand side. So this is also equal to 0. We put that there. We note then that we could group this one more time because A plus B sine theta is in both of these terms here. So PA prime minus PB prime plus, now I'm going to group this and say gamma BR minus gamma CCl4. We multiply by A plus B sine theta equals 0. So that looks simplified. The problem is we are given that this change we said was 0.1 psi. We know gamma, we can solve or calculate the brine specific weight, right? We were given that the specific gravity was 1.1. I gave you this value here at the top. So we still have two unknowns, A and B, and we only have one equation here. So we have a little bit of a challenge. But what we can do is go back up to this relationship, basically, and say that A plus B sine theta is equal to a slightly different version. We can relate it now to our delta L from this interaction up here. So from this, we're going to say, sorry, I've kind of run out of room, but basically I'm going to multiply through by my sine theta to put to get this in terms of A time plus B times sine theta. Okay, so what we can do when we do that is basically we end up with delta H or delta L, pardon me, times the sine of theta is equal to A plus B sine theta. Okay, so now we can plug this in with only one unknown. So this becomes, let's see, I think I provided myself some room on the next slide, so I'll give you guys a second to catch up. And then I'm going to go to the next slide and write this out with this substitution in. So we're going to replace this now with delta L times the sine of theta.
Excuse me, Professor?
Yeah.
I think you may have corrected it in the second line of the calculation, but in the first really long line where you wrote it out, the last term, is it supposed to be plus gamma BR B sine theta? I think you fixed it on the second line.
Let me see. So this one, let's see. Can you see my cursor?
Yeah.
Okay. Is it this term you're looking at, the negative?
No, one more line of calculations down. It's the last plus gamma BR B sine theta. I think it's supposed to be plus there because it was a negative gamma BR times a negative B sine theta.
Thank you. So it's this guy right here.
Yes, I think you fixed it in the second line, but
thanks. Yeah, I think let me see. I just wrote it the wrong way. So yeah, thank you for that. Let me see. I did have it correct on my notes. I just didn't copy it correctly. This should be a plus. Okay. Everybody, hope you can see that. Or hope that was clear. Thanks, Grady. Appreciate it.
Thank you. Okay.
So now on the next slide, then this calculation then comes out to P A prime. So the new pressure at A minus PB prime, the new pressure at B, plus we had grouped gamma brine minus gamma of our carbon tetrachloride times, now I'm replacing, we have here delta L. Sorry, I had used H in my notes, and I'm trying not to use that for you guys because we're working along the length here. So I'm going to say delta L times the sine of theta equals 0. And what we know now is, remember, this is equal to 12 inches. Okay, that's what we were given. This is equal to 0.1 psi, and we're solving for theta. So let me rearrange this and say that sine theta is now equal to minus PA prime minus minus PB prime over gamma brine minus gamma carbon tetrachloride times delta L. And now we can basically write out the values here. So this is now 0.1 pounds per inch squared in the numerator. That's a negative in front of that. And then we divide by, in the denominator, we're going to have, I'll go ahead and make these brackets because we're going to have 1.1 times, this is the for the specific gravity of, or specific weight, pardon me, of the brine. We have the specific gravity times the specific weight of water, and in English units, that's 62.4 pounds per foot cubed. Okay, and then we subtract the specific weight of carbon tetrachloride, which we said was 99.5 pounds per foot cubed, and then I close that bracket, and then I need to make a few conversions here. So what are my conversions? I'm going to just change my color here. Here in the, I've got inches in the denominator here and feet down here. So I need to make a decision about that. Oh, I forgot about my delta. Sorry, let me go back to my red pen. I forgot about my 12-inch delta L here. Okay, so yet again, this is another reason I need to make a change, right? I've got inches in the numerator, feet in the denominator, and inches in the denominator. So what I'd like to do is just go ahead and convert everything to feet, square feet or feet length units. So when I do that, I can, let me do my conversions. I'm just going to show those in green. Come on now. Pen color. Oh no, let me do blue Forgot that green doesn't show up. So this is 144 inches squared per foot squared. And then down here, I'm going to note that 1 foot is equivalent to 12 inches, right? So what that's going to let me do is cancel those units so that I end up with feet squared in the denominator. And then this inch and this inch will cancel so that when I work this out in pounds per cubic foot, I multiply by a foot or feet, and I'll end up with pounds per square foot. Okay, so this should all work out if I just keep working here. Basically, I come up with, where's my magic number here? I end up with, remember on the left-hand side, we just have the sine of theta. But when I work all this out, I end up with a ratio or a fraction 0.466. Okay, so now I just need to find, or basically solve for theta being equal to 27.8 degrees. So I would just do that by, looking for the inverse sine here to give me what sine value or what angle gives me a sine of that angle of 0.466. It should be 27.8. Okay, so that was a long process, I realize, perhaps a little bit painful, but the idea was that we are still basically doing the same thing we did on the YouTube manometer, but everything is not perfectly vertical. We have to work with our trigonometry there. All right, any questions on that? Okay, let me go ahead and get our poll going. The next slide I have is a poll question here. All right, so here's another YouTube manometer, but just a simple sort of gut check here on what should happen in this system, okay? The previous problem, we kind of worked through all the math, but let's just start with a really simple approach, or go back to a really simple approach. There's a reservoir on the left-hand side. We have a manometer on the right-hand side, and you can see the manometry fluid is mercury. So if we add water to the reservoir and we raise the height of the water on the left, what will happen to H sub W? Will it increase or decrease? All right, I've got the poll open now. We'll go for 1 minute. The question is essentially getting at this difference. So you can see HW on the right-hand side here. It's what is happening to this distance which is in part driven by the difference here and this difference here. So HM is indicated on both of these. HW is sort of the split between, but you can see it comes up to this value here. All right, so go ahead and vote. The answers are A or B. It will increase or decrease. We got about 20 seconds left. I'll bring the poll down onto this slide so you guys can see it. It's another 10 seconds. We're only up to 80 students and 80 responses. I think we should have.
I'm not seeing the. Oh yeah, there it goes. I just got it.
Okay. I'll give it a couple more seconds here.
Yeah.
We have 89 folks, so we should have, 86 responses, hopefully. Before. All right, we've got another one in here, so later in the slides. So let's take a look. All right, we'll go ahead and end there and take a look. All right, 55 of you said A, it should increase, HW, and 28 of you said B, it will decrease. So in this case, we would expect HW to increase if we add water and add height on the left-hand side. Now, this is just sort of a gut check. We're not going to go through the math to demonstrate that, but essentially there will be both the HMs will both increase a little bit, but remember they're increasing very slightly compared to HW simply because they have a much higher density than water, right? The mercury does. So they won't change their position quite as much for a big change in the pressure that's coming in for water. Okay, great. Let me go ahead and move that out of our way. Oops. Oh no. Oh no. Okay, good. I was afraid I lost it in between the two screens. That would have been bad. All right. Let's go on to the next problem. Okay, so recall that when we're looking at the submerged gates or we're looking at forces on the planes, we are going to determine two things. We want to know what the resultant force is on that plane or some part of it. And then secondly, we want to figure out where that force is acting. So remember that we determine the resultant force. And this is from your notes last week too, so you don't feel like you have to recopy it. But essentially, the depth range, I'm going to say, of interest. And what we mean here on the left-hand side is, we would go from this value of depth to this value of depth, right? These are H values that are related to the surface of the interface of the fluid with the atmosphere. And below that free surface, we know that pressure increases linearly with respect to the specific weight. So this is some depth range of interest, number one. Number two, we would have the specific weight. I'm writing in lowercase there again, sorry. Specific weight gamma of the fluid in which the gate is submerged. And then finally, just given this example on the left-hand side, the area of the gate, right? And then when we want to figure out where F of R is acting, we would change this up slightly by just saying that we are going to determine the line of action from this reference location here by calculating the distance to the centroid. The centroid of the pressure acting on the gate. And remember, we called this Y sub C. And then we also want to calculate the moment of inertia. Of the shape of the gate. So that should be a P. Shape of gate, and or dependent on the shape of the gate. And in this case, that's going to be Y sub, not Y. This is I XC, okay? All right, so let's take this to heart here, and in the next problem that I have set up, let's work through figuring this out for the given situation. All right, so we have a homogeneous 4 foot wide meaning into the screen or into the slide here, 8 foot long. So L1 over there is 8 feet is equal to L1 right here, okay? A rectangular gate weighing 800 pounds is held in place by a horizontal flexible cable as shown in the figure. Water acts against the gate, which is hinged at point A. So down here at the bottom, we have the hinge. Friction in the hinge is negligible. The question is, determine the tension in the cable. In other words, what is the force acting in the direction to the left here such that it offsets some FR acting in this direction and the weight of the gate itself. All right. So our fundamentals, if we go back to statics, we said that the sum of the forces in the X or Y direction will equal 0 for the static situation. sum of the moments should equal 0. That's going to be useful here. Again, whenever you see a hinge, you should start thinking about sum of the moments. And then in this case, we can work with this planar surface here to figure out the hydrostatic pressure and resultant force that's acting on the gate. Okay. L2 we're going to estimate to be 6 feet. In other words, for this 8-foot length of the gate altogether, we only have water filled up 6 feet along its length. Okay. Now that's not the same as the depth. The depth is something different. This is some h that would be different than L2, our value of 6 feet for that length. All right. Okay. So. And one thing I didn't give you in this, sorry, theta in this case is going to be equal to 60 degrees. So we wouldn't get very far if we didn't have that known quantity. In this case, we would have too many unknowns. All right, so we need to work with some given angle for the geometry here. All right, clean up my mess here. All right, so let's first go ahead and draw a force body diagram here for our gate. We said that we had tension acting in this direction. We said our angle was 60 degrees. We have we also have weight. We know that weight is acting downwards vertically from the center of this 8-foot long gate. We have some FR, resultant force from the water pressure acting, and this is our hinge point A. And I'm just going to call this, let me just make sure I get this right with my notes. I'm pretty sure I just called this L, some distance. Yep, this is some distance L. Okay? And we need to differentiate a couple of things here. And this is part of the reason that I chose this problem. So first of all, I'm going to start with the moments and simply state that the sum of the moments, I wanted to write force, some of the moments about A are, have to sum to 0. And when we write these out, we would say that we have T, the tension, acting in this positive direction. I always use my right-hand rule. When I have the forces going over in this direction, it's going in the positive, it's coming towards me. When I have forces going in the other direction, when I wrap my fingers around, they're going in the opposite, that moment is going in the opposite direction. So T here multiplied by some L1, in this case it's 8 feet, but I'm just going to write L1, and then times the sine of 60 degrees. Now, the reason I have that is that, remember, we only want the component of T that's acting perpendicular to our gate. All right, so we're going to use just the sine of 60 component of L1 times T, right, or the of T itself. So then we'll subtract the weight. And in this case, the weight is going to act, the total height of this, or total length of this gate is 8 feet. So it's going to act at 4 feet away. Right, so 1/2 of that 8-foot length. And now the component that we want here is the cosine of 60 degrees. Okay, that will give us the component that's acting in this direction for the weight. All right. And then finally, the last moment we have to worry about comes from the force, the resultant force here, FR, and it's got some length L away from our hinge. All right, so let me rearrange these. So we said that this is equal to 0. Now I'm going to substitute in just a couple of these things so that we can start to work through this. But I'm going to put T times times 8 feet times the sine of 60 degrees is equal to, so all of this stuff, these other two negatives on the other side will make positives. So then we say W, actually we were given 800 pounds. So this is 800 pounds times, we said half of the length of the gate, so 4 feet, times the cosine of 60 degrees. Let's see if I can write slower to have less of these problems. Plus then the resultant force Fr times some length L. All right, so we are given everything on the left-hand side except T. So we can solve for T. That's ultimately what we want to do. But can we calculate Fr and L? So let's do that on the next slide. Now the resultant force will be pretty straightforward. L we're going to figure out by thinking about those y's, the y sub r. But remember that if Fr is acting somewhere here, when we start to think about these distances down and so forth, we're going to want some y sub r, and L is going to be equal to, in this case, 6 feet minus y sub r, that distance to the resultant force. Okay. So let's look at this on the.
Do you mean 8 feet rather than 6 feet right there?
No. I do mean 6 feet, and the reason for that is that the water is only interacting with 6 feet of the gate. So that's a good point. I'll go over that on the next slide. But yeah, great point. In fact, that's why I brought this out, is because I wanted to make sure that we had an understanding about what is 8 feet and what is 6 feet because of the interaction with the fluid. Yeah, great question, Brayden. Okay, so let's start with our fundamentals. We said that our resultant force is equal to, in this case, we know we have water, so the specific weight of water times some depth of water that interacts with the centroid of the part of the shape that is of the gate that is interacting with the fluid, and then times A. This is, I'm going to call AW. So this is getting back to Braden's point. H sub C, let me just write this out. H sub C is the depth to the centroid of water acting on the gate. And because of that, we basically only consider the 6 foot length, not the 8 foot length. So sorry, let me finish this then. So H sub C is going to be equal to L2 over 2 times the sine of 60 degrees. Now, you may wonder, why did we have to add the sine of 60? Remember, the H's are the depth from the water surface down. We're not worried about Y's yet. We'll get to the Y's that are kind of on the outside, are referenced along the length of the gate in a moment. But for now, this basically comes out to 6 feet over 2 times the sine of 60 degrees. Okay, so that'll be 3 feet times 60 degrees essentially. AW, the force, the resultant force, is only interacting with, we said that we had a 4 foot width times L2 in this case, which is 6 feet. So 4 feet times 6 feet comes out to be 24 square feet. Okay, so we've got just about everything we need. The other thing that I will just note, that if you went to look it up for sort of standard temperatures, we would end up with a specific weight of water of 62.4 pounds per foot cubed, multiplied by 3 feet times the sine of, sine of 60 degrees. 60 degrees. Okay, slow it down. And then we multiply by 24 feet squared. Okay, so that was okay. When we work this out, we end up with 3,890 pounds. Okay, so there's our resultant force only from the water pressure acting on the gate. So only over that 6 feet by 4 feet area. All right. So we found FR real quick, just going back to this previous slide. We found FR. We need to now figure out L. Okay, so that we can solve for T. Okay, so what is lowercase l? I just realized I made a bit of a boo-boo. To give you all just a heads up, on the right-hand top corner here, I'm going to have a little image pop in just a moment when we're working through the geometry, and I forgot that that's going to cover over what we have right there. So my apologies for that. But let's start with figuring out L. L is equal to what? That was supposed to be a question mark. All right. L, we're going to say, is equal to some L2 length minus this y sub r value, okay, which is this reference length to the location of action of FR. All right. Now, this is, we already know what L2 is, so we can write this out to be 6 feet minus y sub r, and y sub r then is the value that we need to solve for to basically figure out little l here. All right, so our generic equation that we wrote in class on Thursday said that y sub r, no, that's supposed to be an r, gosh, okay, is equal to y sub c, c plus the ratio of our moment of inertia, depending on the shape we have, that's interacting with the water or with the fluid, divided by the product of the location to the centroid times A, in this case, AW, right? We still are not considering the full area of the 8 foot long gate, only that interaction of the fluid with it. So 6 foot long by 4 foot wide. So y sub c, what am I gonna do here? I'll just do this here. I think I can just squeeze it in. Y sub c is equal to, in this case, 6 feet divided by 2 to get to the middle of that, of the interaction with the gate. So that would be equal to 3 feet. So that's to the middle of where the water is acting with the gate. And then y sub r is equal to 3 feet. Oh my heavens, this is rough. Okay, 3 feet plus. Now we need an equation, all right? And this is where this popping comes in. I apologize, I forgot that was there. Oh, we can't see that at all. Okay, what I brought this in just to remind us of what happens for a rectangle for the moment of inertia. So I'll write it out, but otherwise you'd be able to see it under there. But IXC is basically equal to 1/12. Oh man, 1/12 times the width of our rectangle, so 4 feet. Wow. Christmas. All right, times, and then the height of that rectangle, so 6 feet. Really? Oh. Pulling out the eraser. I don't like this. Erase pen. Oh, that got rid of all the pen. All right. That wasn't cool. Okay. Sorry about that. Okay, so where were we? We were figuring out y sub r was equal to y sub c. We said y sub c was equal to 3 feet. Y sub r is equal to 3 feet plus 1/12 times the width we said is 4 feet times the height of the rectangle interacting with the water is 6 feet, and we're going to cube that. So this is IXC, and then we divide by y sub c which was 3 feet, and then the area, which is 6 feet times 4 feet. Okay, when you work this out, you basically get y sub r being equal to 4.0 feet. Okay, so we said that little l was equal to 6 feet minus y sub r. So this is equal to 6 feet minus 4 feet. That equals 2 feet. I guess actually I should have just left that at 2 feet rather than 2.0. Okay, so now we have L and we have F sub R. So we can go back to our moment equation and solve for T, the tension in the wire, the cable that's holding up this gate. And so when we do that, I really thought I was just going to be able to erase and not erase all of the text there. Sorry about that. If you need to catch it, I'd recommend going back to the video. Okay, so on the next slide here, we will just solve for T is equal to the 800 pounds of weight force times 4 feet times the cosine of 60 degrees. So remember, the weight force is acting with respect to the centroid of the entire gate, right? That's where we got 4 feet from. Plus, then we have the resultant force here, 3890 pounds times 2 feet, which is where it's acting. That's little l, and we divide by the 8 foot length. 8 foot length and the sine of 60, which basically allows us to work in the right direction for T, and T comes out to be 1,350 pounds. Okay. All right. I realize we're a few minutes over, so the last thing I'm going to do, I'm just going to give you about 20 seconds to catch up there, and then I will do one last clicker problem real quick, and then let you guys go. So my apologies for this not working out quite the way I was hoping, time-wise. All right, and we will do the other 2 problems that I have set up. We'll do those in class tomorrow as we talk about one new concept. All right, so the next slide here. We have this, a system that we've seen before. The question is, in the diagram on the right, P is a force that holds the gate shut. If we add water to the reservoir, in other words, we increase the depth here, and the gate gets further and further down, or deeper and deeper, will P need to increase or decrease to keep the gate shut? So the answers that you're looking for are A or B here. We're up to 20 seconds. I'll let this go for a minute. Again, I apologize for keeping you guys past 5. But after we finish this, I'll let you go and we'll work on these other problems tomorrow in class. 51, 53. Okay, about 15 more seconds here. See what we get. All right, plateauing a little bit. How many people do we have left? We're at 66, so we've dropped a few. Okay, 63, that's about right. Okay, so let's take a look at what we got. 58 of you said we need to that P will need to increase to hold that gate in place, and 6 of you said it can decrease and still be held in place. The answer, if we increase the water and basically increase the pressure, and therefore the pressure force acting on the gate, regardless of its shape, P will have to increase to hold and counter that resultant force if we increase the depth of the water or further put that gate further underwater to hold it in place, to keep it closed. Okay, thanks for a good Monday afternoon, and I will look forward to seeing you all in class tomorrow. Take care.
Thank you.
You bet. Thank
Thank
you.
you.
Thank you.